Okay, welcome to Unit 24 of the course on mathematical methods for signal processing. And as an introduction, I'm showing you a plot that I will use later on of a very simple signal which is fairly well concentrated in time and frequency. So you see on the left upper corner the signal, real part, imaginary part in red. And this signal can be periodized. So when people start to do Fourier transform, they very often refer to it as letting the period go to infinity. So I had to fit everything into the picture. So I was taking the three periods out of this. So of course I was just convolving with the Dirac comb with 3 Dirac spikes, or I was shifting by 1/3 of 480, which is my signal length, which means simply I'm shifting the original version by 160 to the right and to the left, or 2 times 160 to the right. That's the same as negative, of course. Now, in the same way, you can also sample the function, and I was choosing a sampling rate of 2. And of course, you can sample the periodized version. Of course, these things are kind of commutative, so you can choose the order if the sampling rate and if the period is related to each other. So in my case, sampling rate is 2, period is 160, so that's clearly no problem. Now, what the picture to the right should show you, the right lower corner should show you, is the left object, so the periodized and sampled version of the function, has a spectrogram which looks very nice. It looks like something living in a circle. That's actually how I was creating this. It's a certain linear combination of Hermite functions, but that doesn't matter. And you see 3 copies along the line and 2 copies because the upper and the lower part are just half of one individual part. So you see that you have essentially 6 copies of the original spectrogram. Now imagine a movie. I cannot do this here, but imagine that the period is going to infinity, so your window would be bigger and bigger, and these left and right copies would move to infinity. The sampling rate would be smaller and smaller, so the objects here would move. And eventually the person who's watching this interior, so the essential part of the spectrogram, the short-term Fourier transform, would say, oh, I'm fine, I'm seeing everything. That's related to my story that you're buying a CD with 3 minutes and sampled version up to 20 kilohertz. And you're saying, that's fine, it's perfect, it's the original music, I cannot distinguish the difference. So this is another way to visualize the weak star convergence. So weak star convergence in a 0 prime looks somehow weird, but at the end it's nothing else but saying, well, if I concentrate on the rectangle in phase space, or in this short-time Fourier transform domain in the time-frequency plane, can I get a good approximation of what I really think is the truth? And that would be, in this case of an ordinary function, an ordinary nice short-time Fourier transform. And of course, this is a decent function which is both decaying in time and frequency very well. So it's actually a Schwartz function, but for us, it's a function in S0. And that means that this is a plot of actually only the absolute value of a function in S0. And we know that this is meaning it's well concentrated or so. So this is the background of what I'm trying to explain today, which is I want to talk a lot about it, about discretization, periodization, periodic convolution, and so on, and we will see how far we get. Now, one other thing that I would like to mention is let me share this other screen, is that you should feel that you're now in the situation that you have understood the basic things. So we have a lot of terminology, a lot of function spaces or so, and it's like you have arrived in a new country. You know a little bit about the language so that you can learn, you can ask your questions, You understand the problems. Of course, you are not perfect in the new language in the new country, but you have some orientation or so. And that's why I think my plan is for the remaining few sessions to just show you how to use these tools and not be so strict anymore. Well, I think it's like instructing a person to come to a new country. You have to do all the details correct to reach the country, to have the right permissions, and to know basic terminology in order to help yourself. But now we kind of explore this new country, which is for you the mathematical world of signal processing. Now, this last thing that we were discussing, and I don't want to repeat it in detail, is this idea with a 1 point or with characterization of the spectrum, and then the extra question, if you have an individual point separated, so the support of such a mild distribution is a single point, and then the consequence is then it's a multiple of a Dirac measure. So you have already understood that Dirac measures and pure frequencies are the building blocks of Fourier analysis. And so it's quite good if you can reduce things to this, and clearly a Dirac measure has a support which is exactly the point, which is in the label. And so to be able to come back is something which is quite nice, and a special feature of this theory of mild distribution. Just recall once more that in the setting of temper distribution, you can have derivatives built in. So functional picking out of a polynomial, the second derivative at some point, it's quite fine. It's applicable to Schwartz distribution, to a temper to Schwartz test functions. But in our situation, we don't have it. The local structure of a zero space is the local structure of the Fourier algebra, which is quite intricate, but it's not involving any real smoothness. So derivatives don't exist, is something in the background of this story. Now we had the proof, and I don't want to go into this detail. The main point was in this ideal of functions which vanish at a given point, and we can reduce everything to zero, the elements which have disjoint support, disjoint compact support, so where you are making the zero a little bit broader and have a zero near the point, can be used to approximate. There was this game with the bounded approximate units in this ideal and that itself allows to bring in the maximal ideal stuff, Massur's theorem or so whatever, which allows you to come up with this conclusion. Now this is a local result, only a single point, and therefore I would like to extend it, because it's very useful and important, to more general situations. So these more general situations cover the case of lattices. So a discrete set which is obtained by applying an invertible matrix to the standard lattice, which is set D, the integer coordinate systems, is a special case of what I'm discussing now, because I would like to give up this regular algebraic property. So we can take discrete measures sitting at points which are from a collection of points which is discrete, but in a little bit better sense with some eta separation. So if you give me some positive number, let's say eta is 1/2, then I'm saying this discrete set is eta separated if the distance between two different points from this discrete set is at least 1/2. And of course, that means that you can make circles of radius 1/4 around each of these points, and this will be disjoint. Now, I'm not sure, but I probably can try to show you a few pictures which I've produced over the weekend. Yeah. Here is a collection of points which is not, which was meant to be not exactly separated, but the union of two separated sets. So I have a small MATLAB routine built over the weekend to create delta separated sets. So that means I'm taking random points. And if the point is too close to any of the earlier points, I throw it away. And if not, I accept it. And then I was making balls. You see in this part here, this point is well separated from this. Maybe this is also okay, but here, this pairwise, they may be closer. So actually, I was taking a union of two separated sets. So what I will say is essentially also possible for such finite unions. Sometimes people call such sets well-spread sets or so, but it just happens that this plot is coming earlier, but first I should have shown this here. This is a not regular, because there's no lattice attached to it, but a separated set. And you see here, essentially what you have to do if you have a finite set, it's always eta separated. You go for the minimal distance, and if you take the minimal distance, then you can make a circle of half the radius, and they will touch maybe, but let's say they are open circles, then they are disjoint. Now, I could play a game, and that's the essence of what we are doing here, and ask you, well, if I give you the radius of these blue circles, and I give you a big circle, which is the fixed radius, how many red points can you fix? And you will say, oh yes, I can put something here or so. And then I might say, well, but if you're careful, instead of putting a point in the middle, maybe you can do then more dense packing and fit in 3 or maybe even 4 points. Yes, if you start here, probably you can put 4 points here, or you shake it a little bit and so, but I'm not going for an algorithm, but I'm going for the simple evidence that the number of red dots that you can place inside a circle, as long as these blue circles are disjoint, it's clear that the blue marked area, which is the number of points times the area of a little blue circle, can be at most the total area of the circle here. Now I have marked 2 circles here. Maybe in this example is not so clear. I would say all the red points should be inside of the black circle, but if a point would be a little bit more to the boundary, it clearly would be inside of the red circle. So that's just enlarging the radius a little bit allows you to say, I'm not counting the points inside the black circle, but I'm counting the blue disks inside the slightly larger radius. Now, the main point of this here is the area of all these objects, the circles, the small and the big ones, are uniform over all the positions. So you see, I didn't mark any coordinate system, and you don't need to see a coordinate system, and that's how you can estimate the number of points. Okay, let me see. I think I have, another picture which is maybe better. Here I'm having the question of how many points can a eta separated set have inside a given circle, and the answer is, well, replace the black circle by a red circle and make the little here probably I took maybe not eta 1/2 but maybe eta 1/3 or so, and make this, but the number can be controlled. So this is the key of my argument. Now let me come back to the. So if the statement is the following, and I hope you can see now proposition 23. Assume I'm telling you that I have or you are telling me that you have a mild distribution, but somehow you have recognized that support is a eta separated set. And then, of course, you expect that if you look locally, you find only Dirac measures, but the next thing is that you would also find that these coefficients that appear with the point measures are uniformly bounded. So mathematicians would say the sequence of coefficients is in L infinity over the set X. But conversely, the following is true. If you tell me the eta, I can compute a number, and that has to do with the number of points in the big circle, blah, 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 such that any measure, which is this, we call this still a measure because locally it's a sum of Diracs, and therefore it's a little bit better than just a distribution, is a bounded linear functional on the Wiener algebra, and therefore, of course, also on S0. So the sigma can be controlled in the dual space of S0 by the duality with respect to the Wiener algebra, which is a little bit more kind of, less sensitive. And this one can be controlled by this. And this is true for every eta separated set. And of course, if you're not caring about the constant, you can take any finite union of eta separated sets. And that's why I was showing you this plot with the pairs or so. Now, I'm not going through the technical details, but want to discuss the key features of the proof, so that you can, when you study it, you understand what's going on. So I have the information that you have given me that the set X is eta separated. Okay, so eta is given. And I choose now some radius, that's kind of the radius of this little yellow balls, such that if a point is such, well, if we have two index sets now, we have the points which are labeled by xj, and we have our fine partition, a very fine partition, which is a delta fine partition, such that the psi I are little bump functions, and you are telling, or we are looking at one situation where you say, okay, at point number 5, psi number 100 is not 0 or so. And then the argument is that this same function psi I will only be non-zero at most one of the points. And that argument is very, very simple. If psi I of xj is not 0, it means that this point xj must be in the support of psi I. So psi I is only non-zero in the inside of the support. But that means that the psi I cannot be too far away from the ball of the center. So actually, I think we could have b of delta of xj, but I think that should be a b delta of xj. So it's just saying that the BUPU is having little bump functions supported with, support xj. Yeah, what we have is that, maybe it's a bit too short here, that the center of psi I is a point which normally I would call xi, but I avoided it here. So it's the center, and so the xj is a different point. So let's say within the support there, the distance is about 2 delta. Now I'm just saying, well, for every point in our separated set, we take all the elements from the BUPU, and recall it's a very fine BUPU where this is non-zero. And we just claim that if you choose different points, xj, x5, and x6, for example, then they have no common indices. And the argument here is quite clear, because if you take I think I have to rewrite this a little bit. If you're at the center of the psi with the number I, then the sampling point x with the number j prime, which is different from the one which we have used for the starting point, is at most this distance. So this is the big distance, which is eta, minus the small distance, which is 2 delta. So they are too far away to have some. Okay, so maybe I should try to explain this differently, but at the end it means that you're localizing with your BUPU the sigma is a sum over the psi I, and only the support of an individual one which is, it should be ij here, sorry, should be exactly 1 point. And then each of those points is, by the lemma before, a Dirac measure at the point with some coefficients. Now, the question is, how can we demonstrate that the coefficients are uniformly bounded? And that's very easy. You're just testing this distribution on a set of functions which are in the S0 space and which have the value 1 at those points. So how can I do it? We are starting with the triangular function. That's now one of the last expressions here, delta. We compress it. We get a narrow triangular function, and of course we make it so narrow that it maybe the support is at most delta. So if this function is moved to a point, so we are taking txj of that function, it has the peak of the compressed triangular function exactly at the point xj. So txj of f, or of the compressed delta function, is exactly 1. But on the other hand, if you apply this sigma to this function, you get cj times the value, which is 1. So you get exactly the coefficients cj. So sigma applied to a family of functions is giving you exactly the coefficients. But this family of functions is just the shifts of an individual function. And that means they all have the same norm, and therefore you can find out that this sequence of expressions must be a bounded subset of the complex numbers. And that simply means that the soup over all these complex numbers, Cj, has to be finite. Now, the opposite argument is exactly using these pictures that I have used for illustrations or so. And we just have to recall the atomic characterization of Wiener's algebra. So WC0L1 is one of the characterizations of Wiener's algebra. You take inside of C0 those who have absolutely convergent decomposition with respect to some harmless poo-poo. Now, this means that if you know how to control any of these pieces in the poo-poo, you're fine. So think of R2 and think that your psi j functions are all supported in circle of a fixed radius. Now, if you're finding that you have a measure now, a discrete measure, which has these boundedness coefficients and is living on these points, on the red points, and somebody is coming with an atom, it will be located, concentrated in one of those red circles. So what it will pick up is exactly the absolute value that you pick up is Cj times, maybe you should write absolute value of the function k that you can put, that is this atom. But an atom can be controlled by the subnorm, and let's say for the test case, we would choose this to be norm 1. So each atom is a function living on a red ball with subnorm 1. And if you apply now such a discrete sum of Diracs, you get only finitely many, because independent of the position, that's the main point, there are at most k function, and the k depends only on the ratio of the areas between big red circle and blue small circle. And so you come up to this constant, and clearly this counting effect is a constant depending on your eta. If your eta is small, or if you have finite unions, then of course this will grow, but for fixed eta and for fixed sup over the coefficients, you have this estimate. So we have a two-way direction, and of course what would I say? The characterization applies to discrete measures sitting on a lattice. Now, I have written a few more things very recently, so I think that was the very last thing that I was doing before the start of the course. So let me try to go back. Yeah. I will talk about periodization in the next subsection, but let me just tell you what it means with respect to this spectrum and containment of the support or so. So I recall to you that if you have a distribution which you can shift so that it doesn't notice that it's shifted, so maybe you take this pattern that we have seen at the beginning, you move it along some lattice and it doesn't change, so it's the periodic thing. So a mild distribution is lambda periodic with respect to some lattice, some subgroup now, not a discrete set, but now a lattice, means that you have T lambda of sigma is sigma. Since a group means also the inverse is it, you can also say that you shift backwards, but this is just another element of the group or so. And the claim is that if you do this, if you have this information, then the spectrum, it must be discrete and sitting in the so-called orthogonal lattice. These are all the frequencies. If you look at them on the lattice lambda, you don't get anything non-trivial, so that means these are the frequencies which are constant one for all the lattice points. Just to remind you that if you take the integer lattice, then the perpendicular lattice is just the integer lattice again, so it's set goes to set, and that's a benefit of our choice of e to the 2 pi I with the pure frequencies. If your lattice is alpha times set d, then the orthogonal lattice will be 1 over alpha set d. So making the periodicity, let's say, very dense, then it means you make the orthogonal property very coarse, or, which is maybe the intuitive, more interesting thing, if you're saying, I'm letting the period go to infinity. So you take something, you periodize, and then this periodized version is now a very coarsely periodized thing. Then the lambda will be alpha set d for big alpha, and that means the spectrum is contained in 1 over alpha integers, which will be more and more dense. And so that's the heuristic argument why letting the period go to infinity means at the end, the limit of all this more and more dense is the continuity of pure frequencies that you have in the Fourier transform. But maybe this is a side remark. But now we're able to do a converse. If you're saying, oh, I see a Fourier transform, or I know that the support of the Fourier transform of my mild distribution is inside of a lattice. And for consistency, I call this lambda perp, because lambda perp is, of course, lambda. Then you find out that this is the sigma must come from a periodic thing. So in a nutshell, the statement of the proposition is periodicity on the time side in this world of mild distribution is the same thing as discreteness of the spectrum. Okay, so the proof we'll use facts that I will discuss in a moment, but it's very plausible. If you give me any lambda periodic distribution, then what I use as an auxiliary tool is a BUPU, but it should be conformable with the lambda. So of course, if you get a general lattice, you can get it by distorting the standard lattice. So how can you get a lambda BUPU, which means a partition of unity of the form T lambda of psi for some psi while chosen? Well, you just try to distort a BUPU that you get in the ordinary way. Even if it's in FL1, you can distort it by affine transformation. And therefore, we can have such lambda BUPUs for any lattice that you're giving me. So what the claim is that you can multiply your sigma with the psi. So if you would do it in the real case, I mean the one-dimensional case on the real line, you would say, oh, I'm getting a periodic function, let's say with integer periodicity. So I cut out the part from 0 to 1, or from 0 to 2 pi if you have a different normalization, or from -1/2 to +1/2 or so. And I'm just saying, well, that's a good idea, but it's not perfect. It's better to take a smooth poo-poo, because then the good properties of your overall sigma will be encapsulated better in this smooth localization. So in this sense, we will do this again in a moment in a more general situation. So I call this H sigma, the Fourier transform of this guy. Now, sigma localized is something which is local. So you can always multiply it with some trapezoidal function. So sigma psi is the same as sigma psi multiplied pointwise with some trapezoidal function in a 0. But that means if you go to the Fourier transform domain, sigma psi is, well, a localized version of a mild distribution. It's a mild distribution, that's no problem. But then this tau, which appeared in several proofs already, tau hat will be also in a 0. So we know that this Fourier transform of this local piece is actually a uniformly bounded continuous functions, because we know how to convolve a functional with a test function. It would be a sigma and then applied to the test function f in a flipped version, shifted, and that's giving you a continuous function. Well, if you have the statement that sigma is obtained by periodizing now this localized version of sigma, then it means that sigma is SHA lambda, the sum of Diracs of sigma psi. But the Fourier transform is the Fourier transform of a convolution product. Okay, now this is a typo, of course. I should have written sigma is the convolution product, so it should be first the convolution product, but once I'm writing the Fourier transform, I should already write the pointwise product. So I will add one intermediate term. So sigma equals SHA lambda with sigma psi. Then we take the Fourier transform, which means we have two factors, two Fourier transforms, but a pointwise multiplication. And now comes the general Poisson formula. This is up to a factor, C lambda, which I also ignored, a distribution, a Dirac comp at the orthogonal lattice. And this, by definition or by convention, is a bounded continuous function. So if you have this, then you just multiply out your coefficients at any point of this perpendicular lattice will be the amplitude of H sigma at that point, lambda prime or so. So you get a sum, and the coefficients are bounded because this is a bounded function, so everything is fine. So if you give me a periodic mild distribution by such a very simple computation, which involves this smoothing operation and the Poisson formula, gives you a discrete continuous measure. But now I can go in the opposite direction, and I think that was worthwhile the effort. You have observed that the Fourier transform of your sigma is supported on such a lattice. And then, of course, by what we have already shown in the previous proposition is that then it has to be a sum of amplitudes or so. So a sum of Diracs. Now, if you multiply your sigma hat, remember, this is a sum of Diracs, with certain pure frequencies, which are taken from the original lattice. So you have e to the 2 pi I, and you have pure frequencies which happen to be exactly at the positions that you have here in the support of your sigma hat. They are all 1. So how do you multiply a discrete measure with a pure frequency? You just multiply with the pure frequency at such a given point. But the pairing between lambda in lambda and lambda perp in lambda perp is exactly that. If you put them together, you get 1. So remember, it was if the lattice is alpha times set in 1D, and the orthogonal lattice is 1 over alpha times set. Well, if you take e to the 2 pi I, and the s is, let's say, 1 over alpha times k, and the time point is now alpha times L, then the alpha and the 1 over alpha cancel out each other, and you're remaining with e to the 2 pi I jk or whatever as an integer, and that's 1. So this is, and only if this is true and so on, you have this property. So you get that multiplication with the pure frequency of sigma hat is this. But what is this? Well, this is t minus lambda of sigma is the same as sigma. Remember that t minus lambda goes to modulation on the Fourier transform side. But this is true for every lambda, and that's why I can ignore the minus lambda. I could say it's also true for m minus lambda of sigma hat is sigma, and that is directly going to the shift invariance. So we have a very strong relationship in this way. Okay, now I would like to go to another statement, and that's discussing the periodization trick. Yeah, in today's version, it's 207. And so we will go into more details. I'm not sure, I think I have already explained parts of this, but not well enough. And now in the light of the new theorems, I would like to do it once more. So the target is, and I will continue after the break with this as well, is how do we get discrete or cyclic convolution? And the starting point is, well, let's consider the space of periodic functions in the bounded continuous space. So clearly a bounded continuous function is a mild distribution. So such a bounded continuous function, which is lambda periodic, will be also having a Fourier transform, and we know that this Fourier transform will be concentrated in the orthogonal lattice. And actually this is just another way of saying, well, a bounded continuous function has a Fourier series expansion, and this is more or less a modern way of looking into the classical Fourier series expansion theory. But what I want to do now is, once more, now in the setting of continuous bounded functions, this statement that every function which is periodic, continuous and lambda periodic, is obtained by its localization. So I think, I'm not sure, but and of course, the other thing is, if you start with a decent function, so in this case, it's a Wiener algebra, in particular, if it's in S0, and you periodize it by convolving it with such a Dirac comb concentrated on the lattice lambda, then you're getting a periodic function. So it means the periodization makes function periodic. But every continuous bounded periodic function is obtained in this way and you do it by localizing it with a lambda bupu. So that's the story of this lemma. Yeah, so kind of what brings me back to this story with what will be the basis for the periodic convolution is the following. If you have a bounded measure, I'm not sure if I have really told this, but sorry. If you have a bounded measure mu, which is clearly defining a linear operator, which is mapping the lambda periodic functions into themselves. So yeah, maybe the first thing is you're convolving it with a mu. So what is mu with f from this space? Is it still lambda periodic? Okay, what is T lambda of mu convolved with f? And now we know that convolution with delta lambda is nothing else but shifting. So we're talking about, we are doing a shift, a delta convolution with a mu with a f. And you can choose the order. So if f convolved with delta lambda is already f, of course, by still applying mu to it, it will have the same property. So every bounded measure is is leaving the space invariant, but also if you do any linear combination of your measure. So you shift and you say, okay, I take one shift lambda 1 with amplitude 1/2, another with 1/4, and you have even infinitely many of them, but adding up to 1. So that's why I choose 1/2 plus 1/4 plus 1/8 or so. That would be an infinite choice. And you are saying, well, my integer lattice is the integer, so you do a shift. Then all these things have the same effect, because on the lattice lambda, you can always move the shift parameter to the obvious thing. Okay, so why is this true? And the key point is this. You're doing a convex, we call it the convex linear combination of the shifted versions of mu. And of course, the shift is from the lattice always the same. So what is mu with f? Well, mu is an absolutely convergent sum of shifted versions of the mu. So you can pull this in. So first you have an infinite sum, brackets, convolved with f, but we can do it separately. We convolve the individual parts. But here the shift parameter can be moved from mu to the f. And therefore, all these t lambda k's are the same as the f. And suddenly you have each of these shifts is essentially the action is the same as the action of the mu itself. But you give 1/2 mu plus 1/4 mu, you add up the coefficients. And so you're writing summation over ck bracket times mu, which is of course 1 by our normalization, which is mu with f. So if you have understood this principle, then you can understand that if you are taking now for the fixed lambda periodicity a lambda bupu, as we have done it so often now, and we decompose a given measure into this, then we can do the reverse. We can say, well, mu psi lambda is living near set lattice points 5 to 6, 10 to 12, 10 to 11, 99 to 100 or so, but what we do, we shift them backwards. So we are building, taking all these building blocks, and the part that is living between 5 and 6 roughly, with a little bit of overlap, we move back to 0, 1. The guy at 50 to 51, we move it back by 50 so that it's also living there. And then, of course, this is just the same effect that we had before. Mu convolved with f, well, mu is the sum of the pieces. But we can shift the pieces without noticing. For example, here I was saying I shift these pieces to the left, and at the same time I shift the f to the right. That's a formal thing, because the composition of left shift with right shift is identity. So this is really the same. This guy is really transported and it's moved around. It's a new measure, but this guy here is not seeing it, so that why you can write the f here. And so the nu that we constitute in this way is the sum of all these pieces. But as I said, by shifting the pieces back to the center, they are all living where the psi lives. So as you can see it, it's a product, and the t minus lambda of t lambda of psi is just psi, and it's the inverse shift. So it's like pulling your measure to the localization operator psi, and they're all localized in the same. So what you can say is that the new measure, which we call nu, is a sum of things which are all concentrated inside of the support of psi, and that's a fixed compact set inside some ball of radius r. And so in this way, we reduce this ambiguity and say, well, you can move things around, still have the same action on C lambda, but what would be the optimal concentration or so? Now, the detailed story that I was writing down in detail was, now I'm switching really to functions, so also to be in more traditional setting, and because I found that trying to do it in my abstract setting would be so cumbersome and probably less motivating than what we are doing here, what we are doing usually. So I'm saying, assume that your convolution operator is not just an ordinary bounded measure, but an integrable function. So maybe you think of a Riemann integrable function or so. Then, of course, truncating it to the unit interval. So maybe you think of RD, your lattice might be just the integer lattice, then you would say it's 0, 1 to the power d, or minus 1/2, plus 1/2, taking in every direction. So it would be in the plane, a square of lengths of the side 1 in each direction. And what you're doing here is I'm saying, well, the localized version of my convolver is just make the G periodic. That's what I did before with the measure to localize it, make it periodic and then cut it down. So whereas in the earlier thing I was cutting the measure into pieces, transporting all the pieces, here I'm accumulating the G, let's say on the interval 0, 1, then I add the part which is on 1 and 2, and plus the part on 2 and 3, and so on. So this is really another way of piling up all these things. So you could say I'm taking the BUPU coming from the indicator function of my cube of the fundamental domain, more or less, and periodize it. And then, of course, convolving periodic function with the GQ, and that's well concentrated on the fundamental domain, is the same as the original function. So kind of this is the proof that we had for our measure, so the previous lemma, but now for functions, and with the slight modification that here we're allowed to take a BUPU, which is just a rectangular function and not a continuous function or so. And here are some comments that essentially I'm using that these rectangular functions are a partition of unity, and well, you can be careful and say, well, why did he take the closed intervals? Then you have overlapping points, but then I would argue, yes, this is only true, but on the set of measure 0, and we're working with L1 and then countably many things, or surfaces at the boundaries of our cubes in R3 don't count, or you make it half open. That would be also a way to do this. Now, what is also important is by piling up the pieces at the intervals k to k plus 1 is allowing you to control, I mean, the L1 norm of a function is the sum of the L1 norms of the pieces. That's what we know from the measures. Mu has a norm which is the sum of the mu psi I, and that's just written out for functions here. And clearly, this is the controlling term for our localized function. There might be cancellation, there may be positive and negative values, but this is fine. And so now there is a question of, well, to which extent is this unique? And the answer is, fortunately now it has become unique. So what we can see is we have we're asking the question, now you have two functions, both concentrated on the cube, integrable functions on the cube. You apply them to this lambda periodic f, and you would like to know what it means. Okay, now we write the f itself, because it's periodic, as a periodized version of the local part. So that's the same trick now applied to the f. And then you find out that what has to be true is that G1 convolved with this must be the same as G2Q with this. But here we can use the associativity of the convolution now for our Dirac combs. It means that the G1 convolved with the FQ is the same as the G2 with the FQ. And now if we choose the F to be the pure frequencies, we find out that the Fourier coefficients of G1, you remember now we take it as a function living only on the cube, on the unit cube, must be the Fourier coefficients of the G2Q. And that means that they have to be equal because of the Fourier inversion or the uniqueness theorem or so. So this is a good way to see that if you're acting with your bounded measure or L1 function as a convolution operator on the periodic functions, then you better replace your convolution kernel by convolution with a compactly supported thing living only on the fundamental domain. So somehow this is implicitly already, well, these periodic functions are functions on the torus, so you should take the function on the torus and do the whole theory that we did at the beginning on the torus. So how does this idea of cyclic convolution come in? Well, assume you're giving me two functions, and there is, I would say, there is a q missing, so everywhere. So it's support of, I mean, if the first thing is you're taking the convolution now for the composition of two such operators. Each of them is controlled by a convolution with G1 or G2. Now they're allowed to be different because I'm composing them. They're both concentrated on a set Q. And that means that we have a convolution product, and now the convolution product is not living anymore on the set Q. So maybe you would have a constant 1. Now the constant 1 would be that you're taking you have constant 1 on the set Q. That would be the boxcar function. Now we know the boxcar function in one variable added up with the convolved with the boxcar function would be triangular function. But the triangular function is now living, if you take boxcar on 0, 1, triangular function is living on 0 to 2. It has a peak at 1. And now what you have to do is you have to say, we have to come back to the canonical representation. So what does it mean? You take the G1 with the G2 in any form, but I would say you should take the G1Q. But then you have to periodize and truncate. Okay, what does it mean? Constant 1 convolved with constant 1. Okay, in a discrete game, you would say, go to the Fourier transform. Constant 1 goes to Dirac. Dirac is the unit vector in the discrete setting, multiplied by itself is the unit vector. So it's constant 1 in the compact case, convolved by itself should be constant 1. Yes, this is true because the triangular function here, periodized, is again constant 1. So the trick of periodic convolution is, from our setting, is you're having a canonical representation by something living on the fundamental domain. You're convolving it, but then you're periodizing again and truncating it back so that you get the canonical representative. But at the end, I must admit, it's much easier, much more natural to understand that inside our mild distributions, we have the periodic ones. And the periodic ones can be identified with functions on the torus group, and there it's the natural convolution that we had at the very beginning or so. Last statement before the break, and sorry for going over time now, is we can say, when do two measures have the same action on the subspace of continuous periodic functions? And of course, you can take the same thing with elements in the Fourier algebra and so on, but let's say a sufficiently rich collection of invariant functions. And the answer is, if their Fourier transforms on the perpendicular lattice are equal. And actually, this is what is left over as information when you're periodizing with lambda and then truncating it. So that's kind of another reason. And just showing you once more what we have. If you're saying that I have observed this two bounded measures act on the periodic function the same way. So for all these periodic functions, you have the same thing. Well, we write this periodic function on the left and the right as a periodized version with a decent, well-concentrated function. So probably better take f periodic multiplied with psi. Then we have, of course, that the SHA lambda now moved to the measure has to be the same. That means the periodized version of mu1 has to be the periodized version of mu2, which is this one here, which means that they have the same Fourier transform. But now I'm having the correct notation. This means I'm taking a convolution product, means I'm going to the Fourier transform in the sense of bounded measures, which is consistent with the Fourier transform for mild distributions. So I'm getting mu1 hat, which is a bounded continuous function, the Fourier-Stieltjes transform, times the Dirac comp at this with some factor, but the same factor appears to the left and to the right, so I can ignore it. And therefore we have this. But this is now a continuous functions multiplied with a discrete Dirac comp, and therefore you have to have this. And actually you can also do the converse and say, well, if you have two measures which have the same Fourier coefficients at this level, everything is fine. And now, again, to come back to this story, if you say, but I want to replace them, take only measures sitting on the unit interval on the fundamental domain, then this relationship makes things unique. But if you're not doing it, you can move things around as at the beginning of this subsection of the theorem. Okay, I think I will do a break now and we will resume soon.